All right, so this is lesson 8. So you can see it's talking about the nth term. So what we've been working with is recursive definitions, and the recursive definitions are the ones where you need to know what the previous term, what it equals, before you can find the next term. Okay. What the nth term definitions allow us to do is we can plug in, we want to know what the 10th term is. Well, you can plug in the value of 10 for n, and it'll give you that 10th term. You don't need to know what terms 1 through 9 are. Okay, the equation will find that for you. All right. Now, the nice thing, you do need to know a little bit about the recursive definition in order to get that nth term definition, or at least a little bit about what the pattern is before you can get to that point. Okay. All right, so let's see how to find terms of sequences directly. We're just going to take a look at these four statements. Okay. Now the question says which one doesn't belong. Now, if we had an hour-long class, I'd tell you guys to talk about this between groups of small groups, 2 or 3. Say, try and figure out which one of these doesn't really belong. But what we end up determining, and kind of the outcome of that, is that they all have some similarities. Okay, they all have some similarities. First of all, number 5, they all start with a 5. Okay, each one of these starts with a 5. We actually would end up figuring out that A and B end up being equal to one another, right? Because 6 times 2 is the same thing as adding 6 2s. Okay, 6 times 2 is 12. 2 plus 2 plus 2 plus 2 plus 2 plus 2 is also 12. So these two things end up being equivalent to one another. We also were able to figure out that D, C, and D are equivalent to one another, because multiplying 2 times itself 6 times in a row is the same thing as doing 2 to the 6th power. Okay, so it's the goal of looking at these different expressions was so you can see that the same thing can be expressed a couple of different ways. All right. Now this way, what we end up doing a lot of times, if we're doing a arithmetic sequence, we're adding the same thing each time. That's what A represents, where if you start at 5 and then you add 2 each term, well, you'd add 2 and you get 7, then you'd add 2 and you'd have 9, add 2 and you'd have 11, right? We could represent that. I want to say, what's the 6th term? Well, we could do 6 times 2 because there's 6 2s that we're adding to it, all right? So this is kind of leading us towards what our nth term definition is going to look like. It's going to use some multiplication, even when you're doing an arithmetic sequence. Down here, this is representative of our geometric sequence, where you start with a number, 5, and you multiply times 2 every time to get to the next term. Now, the geometric sequence is going to be represented when we look at the nth term as an exponential, where we have 2 to the number of terms that we have, in this case 6. Since we multiply it times 2 6 times. Okay. So we'll see. My goal for you guys today is to have an idea of how to set up an arithmetic and a geometric sequence in an nth term situation. All right. I don't want you guys to read all this. I'll do all the reading. This lesson that we're doing today, it takes a couple of the previously used situations and it's applying them to now what we're learning today. So if you guys remember, we had that piece of paper that we kept cutting in half. And we tried to figure out what the area of the paper was after we cut it in half. So this one says, Claire takes a piece of paper with a length of 8 inches and 10 inches. All right, now this paper I have here is, this is 8.5 by 11, but pretty close, okay? So 8 inches by 10 inches, and she keeps cutting it in half, right? So 8 by 10, that's an 80. Starts off, that's 80 inches in area. When I cut it in half, that's gonna make that 8 times 5, which is 40. I cut the 41 in half, now it's 20. Cut it in half again, it's 10. And we can keep cutting it in half until we get to, again, I think this one we're trying to figure out what's the area gonna be after 10 cuts. And we can figure that out, right? Instead of writing a recursive definition, Claire writes C of n equals 80 times 1/2 to the nth power. And that's kind of small, I apologize. Where C is the area in square inches of the paper after n cuts. Right? Now, where that definition came from is we know that every next term in the sequence we're multiplying times 1/2. We started with 80, multiply times half, you get 40. Then you get, so we started at 80, we do multiply our first cut, we're gonna have 40, then 20, then 10, then 5, then 2.5. It's getting pretty small pretty fast, right? But we just keep multiplying by 1/2. So if we want to know after 6 cuts, we could do 80 times 1/2 to the 6th power. Because that tells me we do 80 times 1/2 6 times. So they ask approximately what is the area of the paper after 10 cuts. Now, I can't do that math in my head, but I have a calculator either on my phone or in my hand right now where I can do this multiplication. So I can do 80 times, let's see, I'll put the fraction in here, 1/2. I'm going to do that to the 10th power because I want to know after 10 cuts. All right, and I get 5/64. So it would be pretty small. And then we're talking about, this is 5/64 inches squared. So we're talking about something that's going to be probably the size of like the top of an eraser on a pencil. Right? It's tiny. Now 2 says, Kieran takes a piece of paper with the length 8 inches and width 10 inches and cuts away 1 inch of the width. Okay, so what Kieran's doing is actually, let's see, so it's 8 inches long and 10 inches wide. And what Kieran does is just takes away 1 inch of the width every time. So initially it was 8 times 10, but the new one would be 8 times 9. Okay, because we took 1 inch of the width off. And 8 times 9 is 72. Well, then they take, the next item in the sequence, she takes another inch off. Well, now it's going to be 8 times 8, which is 64. Now what's happening, when we take 1 inch off, we're basically losing 8 square inches every time. So we went from 72 to 64, take 8 more off, we get 56, 48. It's just going to keep going down by 8 each time. Now this would represent our arithmetic sequence, because it's going down by a consistent amount. We're subtracting the same amount each time. So even though we started with the same paper, instead of cutting the area in half each time, it's going down by 8 each time. Kieran says the area after 6 cuts in square inches is 80 times 8 times 6. Explain where the different terms in this expression came from. Now, 8 times 6, the reason why is because we're taking 8 each time. After 6 cuts, it's going to be minus 8, minus 8, minus 8, minus 8. Or we're subtracting 8 6 times. So we can multiply 8 times 6 to get that same amount that we're subtracting, right? So that's where Karen came up with that 8 times 6. Write a definition K of n that is not recursive, right? So I want to do an n term. I want to do a term where it's just n. So what I'm going to do is I'm going to say, all right, K of n equals, now you always need to make sure you've got your starting value in there. Now in this case, we're starting with 80. So we start with 80 and we're going to subtract. We're subtracting 8 each time. So we have minus 8 times n. So if I want to know what the area is after 2 cuts, I can plug 2 in for n. 80 minus 8 times 2, which is 16. We will get our 64. For 1 cut, there was 72. After 2 cuts, we were at 64. All right. Now it says, which is larger, K of 6 or C of 6? Well, let's see, our C of 6 is up here. Plug that one back in again. So 80 times 1/2. We do the 6th. I get 5/4 for C of 6. For K of 6, I'm going to type in 6 right there. So 80 minus 8 times 6. That's 32. So 5/4 compared to 32, looks like K of 6 is going to be quite a bit bigger, right? So K of 6 is the bigger of the two after. So after 6 cuts, K is going to be bigger. All right. So looking just big picture, the top example was an example of a geometric sequence. Geometric sequences are going to fall into the exponential equation category, right? The second question here was a consistent decrease, right? This one falls into a linear type of equation. Okay. All right, you guys remember these Sierpinski triangles, right? This is one where we had our recursive definition, right? This is one where every single time we tripled the number of triangles that we had, okay? So our recursive definition was, let's see, I'm going to use S of 1 equals 1. So in the first item of the sequence, we had 1 triangle. To find the nth term, we took the previous number. We multiplied it times 3. So you multiply the previous term times 3 to get the next sequence. Yes?
I was gonna do it.
Yeah, you're good. Okay. So this is how this was our recursive definition that we had for this. Now I want to figure out an nth term definition for this. All right, and I've actually got one. It's on the paper somewhere, but I want to talk about it. So again, the top just details how you get your Sierpinski triangles. Number 1, it says let S be the number of black triangles in step n. Define S of n recursively. Well, we did that. That's what's up here. Number 2, Andre and Lynn are asked to write an equation for S that isn't recursive. Andre writes S of n equals 3n, 3 to the nth power, for n is greater than or equal to 0. While Lynn writes S of n equals 3 to the n minus 1 power, for n is greater than or equal to 1. Whose equation do you think is correct? And explain or show your reasoning. All right. in this situation, they're both correct. Okay? And it's all based on what you're trying to define. Right? In the first one, S of n equals 3 to the n power for n is greater than or equal to 0. If we start at 0, right? We plug a 0 in there for 3 to the 0 power, you're going to get 1. Okay? So if we define that this triangle represents our starting point, not the first thing in the sequence, right? And our starting point would be that'd be term 0. Let's see where I can put this. Let's put it down here. That'd be term 0, right? Then Andre would be correct. Okay, Andre would be correct. If we define this first triangle as term number 1, then Lynn would be correct because 1 is what's going to give us our 1 triangle there at the end because we're doing 1 minus 1, which would make that 3 to the power of 0. Right? Either way, since we were multiplying in our recursive definition, that'll become an exponential in our nth term definition. Okay, so these definitions are very similar. What's not shown in these definitions is our starting point. Our starting point was 1 triangle, and there really is a 1 in front of the 3 to the n minus 1 power. You don't need to show 1 times something though, because it's like adding 0. You don't have to write 5 plus 0. You know it equals 5. Same thing here. 1 times 3 to the n power is still going to be 3 to the n power. All right, we're going to look at both these. So it says pick one of these sentences and write an equation for the nth term. So we'll look at both these. So I want to write C to the n power equals. Now I need to figure out, is this geometric or is it arithmetic? So from 1 to 2, and then 2 to 4, 4 to 8, 8 to 16. I'm not adding consistent amount here because I'm only adding 1 between these first 2 terms. Then I'm adding 2, then 4, and then 8. What am I multiplying? See if it's a consistent multiplier. 1 times 2 is 2, 2 times 2 is 4. Yeah, this is going to be geometric. Okay, this is going to be a geometric because we're multiplying by 2 each time. The way you write a geometric nth term definition, you put the term you start with first, and then you make that multiply what your multiplier is, 2 to the nth power. Okay. So the term you start with goes first. 1 goes first. You then take your growth factor, in this case it's a 2. You're going to multiply 1 times that growth factor to the nth power. So C of n equals 1 times 2 to the nth power. All right? This works, this system, this setup will work for all geometric, right? All geometric sequences. For a arithmetic sequence, which is what the second one is, right? For an arithmetic sequence, I know this is arithmetic because if I go from 20 to 13, I'm subtracting 7. 13 to 6, subtract 7. 6 to -1, subtract 7. We're doing the same subtraction every time, which makes this arithmetic. To do an arithmetic sequence, so it's E, so I'm going to put E of n. Again, you do the same starting point. Wherever you start, in this case it's 20, that goes first. Now in this case, we're subtracting 7 minus 7n. So if I want to find the third term, I'd be subtracting 7 3 times, so it'd be minus 7 times 3. Okay? But this setup is the way you would do all of your arithmetic sequences to the nth term. Now, you do need to know the number you start with to get your nth term definition. Okay? But if you know what you start with and you know what you're either multiplying or adding or subtracting by, you can then get your entire definition. All right. This is the last slide. A sequence is defined by f of 0 equals -3, f of n equals f of n minus 1 plus 0.5, or n is greater than or equal to 1. Now, it says Diego writes an equation for the nth term of the sequence as f of n equals -3 plus 0.5 n times n, for n is greater than or equal to 0. Is he correct? Right, well, let's identify, does this recursive definition we're given to start, is that arithmetic or geometric? Well, it looks like we are. We start at -3 and we're adding 0.5 each time. Well, because we're adding something, that makes it arithmetic. Right? So let's take that. Let's just make our own just to see if it's the same. So we have f of n. We got our starting point, which is -3. We're adding 0.5 each time, and we multiply that times n. So is that the same thing that he got? It does look like it is. Yeah, I think we're good. I think he's correct. Right? And again, he's correct because he's got the correct starting point here, -3. Then he's got that consistent factor that it's being added by, 0.5 times n. Yeah. So again, identify if it's arithmetic or geometric. If it's arithmetic, it's going to follow an exponential pattern. You got your starting point times your growth factor to the nth power. If it's arithmetic, like our second one here, it's going to be your starting point, in this case 20, plus or minus that consistent amount that you're adding or subtracting times n. Okay. That's it. How do you guys feel about that? I mean, we're going to practice it tomorrow. So, I mean, I'm not leaving you guys completely alone from this point on. But I want you guys to, again, I want you guys to be able to identify those recursive definitions, but also those nth term definitions. The nth term ones are really good because they're very similar to the linear and those exponential things we're going to be working with later on this semester.